I wanted to, I know you guys asked for algorithms, but I think this is probably going to be more what you want slash need. We're going to talk about data structures today. So this is the other half of the computer science equation. So if algorithms are repeated steps to get something done, that was our definition of algorithms that we used before. A data structure is a way to store like a shape of storing data and the actions that you can take on that data. So some data structures that we've seen so far: arrays, hashes, objects in JavaScript. All those you'd consider data structures. There's way, way more of them. And like in JavaScript and most like scripting languages, we don't have access to very many. And we don't need them. A lot of the difference between them is like purely performance-y. But you've probably seen some of them before. This morning. Any other data structures you've run across?
Are we talking about like in terms of like, for example, like sorting and stuff, or?
Yeah, it'd be like, so the algorithms are things that you would do to these data structures. So you might sort an array. You might also sort what other kinds of things?
Hash.
Hash is one. Very good. What else? Any others you've seen?
Dictionary.
Dictionary is one. Any others?
Objects.
So a JavaScript object is actually just a hash. Objects in terms of like object-oriented programming aren't really data structures, at least in that computer science sense.
A tree?
Yep, that is one.
Stack?
Mm-hmm.
Queue.
Thank you. Any others? Ever heard somebody say, oh man, this interview was such bullshit. They wanted me to reverse sort a...
Linked list.
There we go. That's the one. Try to think if there's any others that I want to talk to you about. Graph. A pretty good place to start. So actually, I'm going to have to throw a list on here too.
Is network X a data structure?
What was that?
Network X, is that a form of data structure?
I don't think so. Networks are usually structured with graphs. All right, so I'm going to put a couple of these together. List, linked list, and array. And JavaScript land, we use all three of these pretty much interchangeably. They're not the same thing. A list is some kind of collection. Sometimes lists are ordered, sometimes they're not ordered, but we'll call this like sort of a super type. Linked list we'll call a non-adjacent collection of stuff. And an array we'll call an ordered collection of the same type. So these data structures, unlike JavaScript, unlike Ruby, how they work in memory in the computer makes a big difference in how we think about them. So let's talk about arrays. It's a good place to start because we already know a little bit about how to use them. Oops. It's like, why is up and down and left is right? It's because I'm holding it upside down. So let's think of like memory in the computer as just some boxes. Each one of them can store 8 bits or 16 bits or 64 bits or whatever, but they're just they're little registers that we can put stuff in. And like they're physically located on like an actual chip. Not a truck. So like this is a stick of RAM. It's on these little black things, and inside of those, there's just like a shit ton of little transistors. And so like each one of these registers takes up physical space somewhere. So if I want to store stuff in an array, the way it works is that all the things in the array have to be of the same type. That's not a rule in Ruby, and it's not a rule in JavaScript, but it is technically a requirement of this data structure. You'll see why in a sec. If I say I'm going to make an array of strings that's 4 items long, and then I say a string takes up this much space, first string goes there, second string goes there, third string goes there, fourth string goes there. Now here's where this gets fucking dope. So these all have addresses. Let's say for right now, the addresses are just 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, so these are our memory addresses. When I save the array in a variable, it stores a pointer to this. So I might say some array. Oh. This is how you'd write this in like C or Java or something like that. All right, so I want an array with 4 things. Oh, and I need to say the type. So it's a strings. I'm going to make an array of strings. I'm going to call it some array, and it's a new array with 4 places. So in a low-level language, or at least lower level than JavaScript, we'd probably write this declaration like this. Some array is going to be a pointer to 1. And it goes, okay, so a string takes up 2 of these things. All right, you ready to have your mind blown? Oops. So string takes up 2 of these things. So if I want the first item in the array, I'm going to go to where the array is and offset it by, oh, I don't know, 0. And then these 2 things are going to be the first thing in my array. Or maybe I want to get some array at 1. I go, all right, well, some array is at this right here, I know that each of these blocks takes up 2 little spaces in memory, and I want to offset it by 1. So I'm going to skip these guys, and that's going to give me the second one. That number, that index that you've been using this entire time, that's an offset. How far offset from the start of the array is the piece of data that we're looking for? 1 string's worth is what this says. Kind of cool, right? That's a big one. Ask me some questions about it.
That is cool, but as you said, that's not the rule in Ruby and JavaScript. So, if my first index, if 0 is the number 5 and the first index is, a Ben object,
Sure.
I would imagine the Ben object with, 20 keys takes up a lot more space than the number 5.
Yes, you are correct. That's why under the hood, it's not actually an array. An array is more like a metaphor for us rather than something that's actually representing what's happening. So we can use it in a very similar way we could to an array, but it's not actually an array. I don't know what a JavaScript array actually is represented by under the hood, but if I had to make a guess, it's probably a linked list. And here's why. Let's say we do that same thing. We're going to make some memory registers that we can put stuff in. And for this one, these are all going to be different sizes. And in fact, they're not even going to be co-located. They're going to be in different places in memory. So I'll have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. All right, so I've got differently sized things, and they're not all next to each other. So maybe I've got 2 here, 3 here, and like 6 here. So those are the 3 things in my array, my JavaScript array. And these could be anywhere in memory. So instead of like some master list of where all these addresses are, what you do instead is you make pointers. You go, by the way, so this is the first one. This is where the array is, or the linked list. By the way, the next one is kept here. And this guy goes, oh, by the way, the next one is at this address. And then this one doesn't have a pointer, so that's how we know it's the end. And so now, if I have my linked list and I want I give it index 2 or offset 2. You go, okay, well, the thing is here. And so then I jump twice and end up at my thing. Pretty cool. Arrays and linked lists. What are some trade-offs you can think of between these 2 approaches? Why might you use one versus another? This is the array, this is the linked list.
I think you can go straight to a specific index in an array. In a linked list, you have to go sequentially to find them.
Yes. Which, think about when you were talking about big O last time. What's the implication of that?
It's faster.
How much faster?
Would that be O of n?
O of n would be the linked list. The bigger the list gets, the longer it takes us to get to one of the indexes. So it scales proportionally with how big the list is. Anybody know what it is if it doesn't matter? Regardless of how big the thing is, it takes the exact same amount of time.
Is it O of 1?
Oh,
That's exactly what it is. So looking up a random element in an array, we can do in O of 1. Doesn't matter how big it is. Since all these things are in very predictable places, it's the same every time. With this one, the bigger it gets, the more jumps we have to make to get to something. There's no central index of where all these things are. And so that one, looking something up is O of n. But we don't have to have a bunch of memory that's right next to each other. They don't have to all be the same size. So if we have to have some collection of things, linked list might be a better choice.
And wouldn't a linked list be able to hold more because it's kind of like Tetris? You can fit the memory where you have it.
Mm-hmm. In like practical terms, yeah, probably. Ask me more questions about arrays and linked lists.
So at a larger scale, like, wouldn't linked list be better in terms of like, you know, finding and storing stuff?
Not better or worse. It depends like specifically on the scenario. If we have the exact same data type, we probably don't need to take the lookup hit with a linked list. We can just use an array. If they're different types, array is not an option. So we have to do linked list. Now, with a linked list, we've got some limitations there too, where, so I did it this way. This is called a singly linked list. There's also such a thing as a doubly linked list. What if I have to go backwards on this? There's no way to do that. If I want the one before me, I need to go back through all of the other items in the linked list and find the one that has a pointer to me. Yeesh. So each one of these could have, this is the one in front of me and this is the one in behind me. But now I need to store both of those pieces of data. That makes it bigger, or a memory hog. There's also such a thing as a circularly linked list. That means that once it gets to the end, it links back to the beginning. All of those have like costs to them. And so if we were doing designs down at this level, all of those things are trade-offs that have their uses. More questions about arrays and linked lists? Cool. So let's think back to algorithms. What about sorts? Imagine you have to do a sorting algorithm. You can do it for an array or a linked list. Both of those are data structures that you can apply the insertion sort algorithm to, or the selection sort algorithm to. But like lists are a good example. If whatever implementation of the algorithm you're trying to do requires you to know your ancestor, requires you to know the thing before you, not going to work with a singly linked list. Might work with a doubly linked list. Now keep in mind, however you're implementing this algorithm requires you to know something 2 things behind you or 2 things in front of you, this gets just more complicated. It can slow down the performance of it. So like your implementation of your algorithm, heavily dependent on your implementation of the data structure. Another good example, that's a stack. Stack has lots of limitations on it. So stack looks like this. We haven't talked about operations at all. It's a good place to start. You can think of a stack like a collection of plates. There are 2 important operations for a stack. Push, which is adding something to the top, and pop, which is removing something from the top. That's it. That's all you can do with a stack. You can't get the plate at this index. You can't add something to the middle. You can't splice it in. That's not allowed with a stack. All you can do is add something to the top, take something off the top. Likewise, with a queue, you can sort of view this like sideways. So this one has 2 operations also. NQ, which is add something to the back, and DQ, which is remove something from the front.
Could you give us use cases for these different data structures?
Sure. So most of the time, these things get used as parts of like larger custom, more complex structures. A stack. So where have we heard the word stack before?
Stack Overflow.
Stack Overflow. Hey, it's even the logo for it. Look, see, it's piling up, gets too big for the container, falls over. So stacks are super commonly used in, for example, the call stack. Call stack is, all right, I'm going through this program and I assign a variable and then I do this thing. Oh, shit, and then I call this function. So then I'm going through all of the statements in the function. All right, well, then I go back to where I was. So each one of those instructions, as it finds it, it pushes it on top of the call stack. And then when it's all done, it goes, bloop, bloop, starts flipping those things off one at a time. Super efficient way to do that. I'll give you a good example of a queue that I did once. So I was trying to, I was making an app that told me when the train's next to my house and when the buses and all that, like the timetables and stuff. And so the way that I implemented that was I had a queue for the, all right, well, this is the next train, and this is the one after that, and this is the one after that. So like as a train shows up, I dequeue it, and then the next train comes up. And so what I did is I did what's called a circular queue. I dequeued that train, and that's the Monday 2 p.m. train. So then I enqueue that right back on the other side. And so then when Monday 2 o'clock comes again, that one's ready to get dequeued. So super efficient way to do that. So if there's something like, I don't know, 100 bus visits for that particular line, like my entire like data is these 100 events, and I just poop them out and put them right back on the back again.
Are any of these data structures like language specific, or can you can program it in any language?
This is theory. So this is even like beyond programming. Programming is an implementation of these ideas.
Gotcha. Are there like languages that don't support some of like, so for example, what you were talking about with pointers, like how would you implement that with something like JavaScript?
You fake it. So like ultimately JavaScript has exactly one data structure, and that's it's object, it's hash basically. Even like arrays and stuff under the hood are just that exact same data structure. Actually, shit, yeah, I knew that. Yeah, they're hashes under the hood. They're not even linked lists. So yeah, you just fake them out if the language doesn't have the feature. So like if you go to my knowledge wiki, for example, I have JavaScript implementations of most of the data structures. So like this is an implementation of a stack in JavaScript.
Okay, I see what you're saying. I guess doing that's harder if it's not like an object-oriented language.
Yeah, it is. But even if it was like functional, then something like push would also take in the data that you're operating on. But the OOP paradigm is super good for visualizing these. Ask me some more questions about these. Talked about arrays, linked lists, stacks, queues.
So if you're sorting, if you're deciding whether you want to make something a linked list or an array, and you know you're going to sort it a lot, is there a point where it's more efficient to sort a linked list because all you're changing are the pointers and not the actual location of things? Whereas like an array, you would have to actually like reorder them.
That's a good question. Yeah, like I'm a database guy, so who fucking asked me? But that sounds like it makes sense to me. Because otherwise, think about like those puzzles where there's like one piece missing and you can slide stuff around. You're at least going to have one of those as like a temp thing in your array that holds stuff while you're Jenga-ing it. Yeah, versus just changing the pointer values. Yeah, checks out to me.
So this whole time we've been working in JavaScript, I've been kind of thinking that it's using a lot of these structures under the hood, but you're saying that JavaScript in particular like only uses hashes for everything.
Yeah. And like as a like the first level down, I mean below that it's all C and C++, and who fucking knows what they're doing. But yeah.
Okay.
All those things are kind of faked out in JavaScript.
So an array is like a hash with default values. for the keys?
No. So a hash, those things are also, so like I guess a good visualization for a hash would be kind of like this. Okay, so if I got some boxes, so the idea of a hash is we want something that's kind of halfway between a linked list and an array. And so we go, okay, the whole thing is this. This is the hash. Oh, you want to find where something is? Well, I run this little algorithm on the key. And so the keys for these things aren't indexes like 0, 1, 2, whatever. They're things like Ben and Sam and Christine. And so we go, okay, well, if I run that through my little number muncher thing, that's going to give me an offset of this. Oh, and if I run Sam through this little number muncher thing, that's going to give me an offset of this. And if I run Christine through it, well, Christine ends up going here. And then if like you have a collision on that, so like we have two Bens in here. All right, so first Ben goes in here, and after stand-up last week, that's Ben Rowe right now. So Ben Rowe goes in the first one. And all right, so now I'm trying to put Ben Dunn in. And I go, okay, so that goes to the next one over. And so then, like, if I'm trying to get to Ben Dunn, I like the next time I get this, I go, oh shit, there's actually like some space. There's more Bens here, so I have to look to see which one like matches. Sometimes with further hashing. So the idea is that like I have a bunch of stuff, it's stored kind of contiguously, but it can be stored in a bunch of different places, but I get constant time lookup because like I just hash that value and it tells me where it is. True story from like programmers of yore. If you've ever done anything in PHP, you'll note that the function names follow no fucking like consistent logic. Some of them are snake cased, some of them are camel cased, some of them are just all a bunch of words together. Like the reason why that's the case is a real horror story. So Rasmus Lerdorf, the guy who made PHP, was keeping all these function definitions in a hash. And if you get too many that are too close to each other, it slows down the algorithm. So you want them to like naturally space themselves out. So Rasmus was hashing these things based on how many characters were in the function name, and like too many of them had 7 characters. And so he just started using random naming schemes. They had different numbers of characters, and they would end up in different places in the hash. So bad. That's the broad idea there. Ask me some more questions about data structures.
What's a circumstance where you used one of these complex data structures for web development, like role maybe in the industry?
But almost never. Like this stuff, you won't run across it that much in web development. This is pretty like. I would not surprise me if the only place you ran across any of this shit for the rest of your career was in interviews.
I mean, is the DOM not a tree?
It is, but like you're not going to be writing an algorithm to walk the tree.
Gotcha.
Why would you?
Yeah.
It can be kind of helpful to know that. And that can help you maybe optimize something down the road. But if you didn't know that and you just knew how the DOM worked, I don't know that you'd be any worse for the wear.
What about like if you work in the back end side?
Even in the back? Well, I guess, so then it becomes pretty language specific. So if you work in back end stuff, Node also doesn't really have any of these things or get a whole lot of use out of them, because Node is just Chrome's V8 engine. So it works the same way as it does in the browser. Now, if you spend a lot of time in Java, well, Java absolutely has all of these data types and much, much more. And so that can come in kind of handy there because there's performance implications for which one of these things you pick. Now, I would also say if you're doing like web backend stuff, like REST APIs and stuff, it's still not really going to come into play that much. Now, if you're doing like hard tech, like think about all of the things that go into how Uber or Lyft or whoever calculates how many people are on the road, what the pricing should be, like a lot of that kind of stuff, and it needs to do it instantly. Or a search algorithm like Google's search algorithm, where like it needs to be like fucking yotta seconds that you're saving on this kind of stuff. Then by all means, this comes into play. At some point, though, that starts feeling not like web development to me. It feels more like math.
That makes sense.
Because like whoever is working at Google to make something 0.01% faster and it saves the company up $1 bajillion a year, I don't know that they're any like more well-versed in HTTP and like that kind of stuff than like you guys are. It feels like a fundamentally different part of the industry to me.
But this is still the way that memory works?
Yep.
I mean, so this is a terabyte.
Mm-hmm.
So, I mean, that's a lot, you know.
You're telling me, buddy. So let's take a look at Moore's Law. It's been in the news recently because it's kind of topping out. The number of transistors on a microchip doubles every 2 years. And so there you go. Used to take up a room, now it fits in your hand.
Are they like did they came up with this like new way of creating your processors? Like it looks like clear, like, you know, paper.
Mm-hmm.
It's like a film. It's not like
yeah. So some of that kind of stuff is like, I don't know, beyond like my world. But the yeah, they've also talked about like, well, is there a way that is like we're starting to run across like a boundary with how with like some laws of physics on like how quickly the electricity can move. And so I heard some like pop science thing about how like, no, they're going to start using light. And so like, instead of using electricity to like move this stuff around, use light. And like, and that's what fiber optics is. So like that concept works, but like, what if it was doing that inside your computer, man? And so yeah, there's like some of that kind of stuff that's going on. And so yeah, like every couple of years is like, we're sort of topping out on Moore's Law. And Gordon Moore himself, I think, said as much. And like the evidence of that is not like in recent memory, if you weren't buying a new computer every 2 years, you were like streets behind. But that's just not the case anymore. 2-year-old computers are still pretty fucking good. And so like that's like the practical effect of some of this stuff.
If you're curious about chip stuff, I think Scott Singer, who graduated recently, worked at Intel for like 5 years or something like that. He was like a chemical process engineer, I think.
That is sick.
It is sick. All right, so as an exercise, something that might be a good way to work with some of these ideas is try to sort a linked list. And like you can use insertion sort or selection sort or any of the ones that we talked about last time. And then see if you can do the that hard ass thing that this is bullshit. I haven't done this since college. See if you can reverse sort a linked list. So it works just like this. All you know is what the next thing is, but that thing knows what its next thing is. So first, see if you can put something in order that way. Then see if you can put it in reverse order that way. And you will have reverse sorted a linked list. But keep in mind, once you've moved on to a new thing in the linked list, you don't know where you came from. There's no pointer back to you necessarily. So if you do need to go backwards, you have to go all the way through the thing and start over again. Or just go back to the beginning, I guess. So if you want to practice this stuff, that's what I recommend. See if you can sort a linked list and see if you can reverse sort a linked list. And like, this isn't some goofy thing that I made up. This is widely documented. So if you want to see examples and stuff, they abound. In the meantime, what questions do you have for me?
How would you go about like when you have the tree and it's like a sort of like linked list?
Mm-hmm.
Couldn't you just like actually like going backward, just go back to the levels or something, like whichever parents or child it's on?
Maybe. So let's take a look at a tree. Okay, so if we have a tree and we're trying to, well, then we need to like also define what sorted means. So does that mean that like this is 1, 2, 3, 4, 5, 6, 7, 8? So like top to bottom, left to right. You could also make an argument that this should go 1, 2, 3, 4, 5. So that's that like depth first versus breadth search kind of idea. But if you were trying to sort it this way, then similar kind of thing. This node knows what its children are. That's it. This does not necessarily know what its parent is. So it doesn't automatically go in both directions. You could implement something that works that way, but as a concept, it's not a given that you know who your parents are. You do know who your children are. So yeah, I guess you could sort of think of this as a linked list, except you can have more than one thing that you link to.
And you just become more expensive, like if the more information you give to your child, it's more problematic.
Cool. More questions about data structures? Cool. Hopefully this was informative. Have a good time.
Thank you.